Hi, in this video, we will introduce about the sound absorption. In this case, you have a room with no acoustical treatment, and the computer equipment here is producing noise transmit throughout the room. So you can see the sound produced by the computer equipment hit the wall, and part of the energy will be absorbed by the building material, and the remaining sound energy will be bounced back and reflect to the person here. Therefore, we can say this person is suffering the reverberant noise of the computer. Reverberant noise here indicate the noise that is reflected by the ceiling, the wall, or the tiles. So it's a reflection of noise. Besides that, the noise from the computer equipment can also transmit to the worker directly. Therefore, the office worker here is suffering the noise producing by the computer equipment. On the other hand, we have a computer operator here who primarily listen and hear directly the sound from the computer source. From the observation, we can say the computer operator here is mainly affected by the direct noise, and the office worker here is mainly affected by the reflected noise. For those who are suffering the direct noise, one way to reduce the noise is by wearing the protective equipment, such as the earplug or the earmuff. However, it's not practical to ask the office worker that is walking far away from the computer equipment to wear the protective equipment. In order to reduce the noise that is mainly due to the reflection, we can consider to perform treatment to the room by adding the sound absorption material. After you perform sound absorbing treatment to the room, such as the suspended sound absorbing ceiling here, sound absorbing wall material here, and also the carpet with sound absorption. In this case, when the computer noise hit the ceiling, wall, or the floor, most of the sound energy will be absorbed by the sound treatment material here. Therefore, the reflected noise is much reduced. With that, the office worker now receives lower noise level from the computer, and they are not suffer from the noise now. So it's very important for us to design a room with sound absorbing treatment in order to reduce the reflected noise. You need to remember the sound absorption at the ceiling, wall, and also at the floor are only helpful to reduce the reflected noise. However, they are not used to reduce the direct noise. Therefore, the direct noise toward the nearby computer operator here remain unchanged. Therefore, this guy here needs to wear the sound protective equipment to avoid suffering from the direct noise. Before we proceed the sound absorbing treatment, you must know the difference between the free field versus the reverberant field. We have learned the free field previously, where we have a point source. Imagine you are here at the outdoor and there is no obstacle surrounding. So in this case, when you are shouting, the sound will propagate in a spherical format, where you can see the sound is propagated in all the direction, or what we call the omnidirection. Imagine the receiver here is aware with D1 distance from the person who is shouting here. When the sound propagates to the receiver here, this guy listens the sound at 90 dB, for example. So at D1 here, the sound is equal to 90. What if the person here move to D2 distance, which is measured from the point source to this, and then this is the D2 distance, which is double to the original distance. So in this case, what will be the sound listened by this guy? So imagine the sound continue to propagate and hit the second receiver here. So in this case, we know the sound is propagate in spherical wave format, and this is free field condition. Previously, we have learned that for the free field condition, the sound will drop by 6 dB for each doubling of distance. So in this case, if you double the distance, the sound level will drop by 6 dB. So in this case, 90 minus 6, you obtain 84 dB here. So this guy will listen to 84 dB when he is standing at a distance double to the original distance. Imagine the original distance is equal to 2. So when you double the distance, D2 is equal to 4. How if you double the distance again at D3, which is equal to 8? So in this case, when you double the distance, the sound level will drop by 6. 84 minus 6, you obtain 78. So this is the sound pressure level when the distance is equal to 8. So you can use this relationship to predict the sound level at different distance. Bear in your mind, this relationship is only valid for the free field condition. In simple, free field condition occurs when the sound waves are free from the influence of refractive surface. So this means there is no refractive sound when you have the free field condition. For example, the open areas outdoors are treated as the free field condition, like this case, because there are no obstacles surrounding, and therefore there is no refraction of the sound. Besides that, anechoic rooms are also known as the free field condition. An here means without. Echoic here mainly due to the sound refraction. Therefore, together, the anechoic rooms means the room without the sound refraction. So this is the example for the anechoic room. This room fulfills the free field condition because there are a lot of sound treatment on the wall, ceiling, as well as the floor, in such a way when the sound from the speaker here hit to the wall, it will not refract back, but it will be absorbed by the sound material here. Same to the ceiling and also the floor. So when the sound hit to the ceiling, it will not refract back, but most of the sound energy will be absorbed by the sound material here. If this room fulfills the free field condition, we know that for every doubling the distance, the sound pressure level will drop by 6 dB. For example, you are here, listen to the sound from the speaker. So let's say the distance here is 1 meter away. So you listen the sound at 90 dB. When you move to 2 meters away from the speaker, then in this case, the sound will drop by 6, which is 84 dB. So this is the free field condition. So far we have learned that for the free field condition, the sound pressure level will drop for 6 dB every double the distance. If you measure the sound level at different distance from the source, and you see the trend like the curve one here, where the sound level drop by 6 dB per every double distance, and then it remain constant. So in this case, we say the initial part here fulfill the free field condition, and the later part here is the reverberant field. Free field condition here is mainly due to the direct sound. Reverberant field here is mainly due to the refraction sound. Previously, in a free field condition, let's say you are shouting in the outdoor. So in this case, we see the sound pressure level drop with respect to the distance. Every double the distance, we see the drop is 6 dB. At the outdoor, there is no refraction of sound, and there is only direct sound. However, if the person here shout inside a room, so in this case, beside the direct sound, there is refraction sound as well. So this refraction sound will increase the sound pressure level in this region. Therefore, the sound pressure level here is increased like this case, where you see it remain constant after certain distance. So this is due to the refraction of sound. So you can see the D1 distance here separate the boundary between the free field and also the reverberant field here. So this distance can be approximated by using this formula, where the distance is approximate to the square root of A divided by 6 pi. A is the total room absorption, which is mentioned in Sabin. You will learn how to calculate this later. At the moment, bear in your mind, if you increase the sound treatment inside the room by putting more sound treatment material, so in this case, the total absorption A will be increased. In simple, when you increase the A, it means the absorption of the sound increase. By doing this, the refraction sound here will be reduced. So if the refraction sound is reduced, the sound pressure level at the reverberant field here will be reduced to a new level. So after you add absorption, the refraction sound here will be reduced. Therefore, you see the sound pressure level here drop to this level. From the curve 1 here to the curve 2. The new D that is separating the curve 2 boundary between the free field here and the reverberant field here can be computed by using this formula, where you see when the total absorption increase, then in this case the distance that's separating the free field and the reverberant field will be increased as well. Bear in your mind, if you are inside a room with no refraction, then in this case the room is in free field condition. That is represented by this yellow curve. So if you are inside a room with refraction sound, then you will have this curve, which consists of the reverberant field. If the sound refraction inside the room is reduced by adding the sound treatment, such as adding the sound absorption to the room, so in this case, you will experience reduction of the sound pressure level like the blue curve. You must know that the more absorption inside a room, then the less the build-up of sound energy in the reverberant field. So if you increase the absorption further inside the room, then the refraction sound will be reduced significantly. And in this case, you will obtain a new sound pressure level like this, where you see the sound pressure level is dropping. In this graph, you have sound level changed with respect to the distance from sound source. You will obtain the sound level in the blue curve here, which obey this condition if the sound is fulfill the free field condition, where there is no obstacle or there is no refraction. If the sound pressure level is measured inside an untreated room, then in this case, you can expect the sound refract from the wall, ceiling and the floor will be high. So you can see in this case, the sound meets the obstacles such as the wall, ceiling and floor, and there is sound refraction happen. The sound refraction caused the sound level here to be high, although the distance away from the sound source is increasing. So in this case, we call it to be the reverberant field, where you see the sound pressure level remain almost constant at this region. To reduce the high refraction noise, which is approximate to 90 dB here, we can consider to perform treatment. So if you perform the treatment on the ceiling with some absorbing material, you see the sound pressure level is reduced by 10 dB. So if you further to perform treatment on both ceiling and walls, it reduces 6 dB further. If you perform more and more sound absorption treatment by increasing the total room sound absorption, which is defined by the A symbol here, then the refraction noise will be reduced further and further until you see the sound pressure level is approximate to the free field sound pressure level. Then in this case, a room that can fulfill the free field condition is called the anechoic room. Theoretically, if we increase the room absorption, the sound pressure level due to the refraction noise will be reduced. However, in practical, no reduction might be achieved from further sound absorbing treatment. This is due to the limitation of the space to put the sound absorbing material. In many cases, it's more likely you will obtain a reduction of 6 to 8 dB in the reverberant noise.